Light. It illuminates our world. It carries information. It even has the power to heal. But what if we could harness light itself, mold it into a tool of unprecedented precision and energy? This is the story of the laser, a device that has revolutionized science, technology, and everyday life. It is a story of scientific brilliance, fierce competition, and the relentless pursuit of an idea that seemed impossible to tame the very essence of light. From its humble beginnings in the mind of Albert Einstein to its countless applications in fields as diverse as medicine, communications, and entertainment, the laser's journey is a testament to human ingenuity. But before we explore its impact, we must first understand the fundamental principles that make this extraordinary invention possible. This is the story of how a scientific concept evolved into a technological marvel. It is a story that begins not in a laboratory, but in the realm of theoretical physics. In 1916, long before the first laser beam illuminated a laboratory, Albert Einstein, already renowned for his theories of relativity, turned his attention to the interaction of light and matter. He proposed a revolutionary concept: stimulated emission. Einstein theorized that under the right conditions, an excited atom could be stimulated to emit light, not spontaneously, but in response to encountering a photon of a specific energy. This idea, seemingly esoteric at the time, laid the very foundation for the laser. Einstein envisioned a process where light could interact with matter to generate even more light, a cascade of photons all vibrating in perfect unison. This concept of stimulated emission, though groundbreaking, remained largely theoretical for several decades. Scientists grappled with the implications of Einstein's ideas, but the technology to create a device based on stimulated emission seemed a distant dream. However, the seeds of the laser revolution had been sown, awaiting the right minds and the right moment to sprout. Decades after Einstein's groundbreaking work, the first experimental evidence of stimulated emission emerged from the laboratory of German physicist Rudolf Walter Ladenburg. In 1928, Ladenburg, while studying the properties of neon gas, observed a phenomenon that had eluded scientists for years. He found that under specific conditions, the presence of light could indeed trigger excited neon atoms to release more light of the same wavelength and phase. This observation, though significant, did not immediately lead to the development of the laser. The technology of the time was not yet sophisticated enough to harness the full potential of stimulated emission. However, Ladenburg's work served as a crucial stepping stone, confirming Einstein's theory and inspiring further exploration into this intriguing realm of light-matter interaction. The mid-20th century witnessed a surge in research on microwave technology. In 1951, American physicist Charles Townes, drawing inspiration from his work on radar systems during World War II, conceived of a device that could generate and amplify microwave radiation using stimulated emission. Townes, along with his graduate students, embarked on a mission to bring his idea to life. In 1953, they successfully demonstrated the world's first maser, an acronym for microwave amplification by stimulated emission of radiation. The maser, operating in the microwave region of the electromagnetic spectrum, proved that stimulated emission could be harnessed to create a coherent beam of radiation. This breakthrough, though a triumph in itself, also served as a crucial precursor to the development of the laser. Gordon Gould, the man who named the laser. As the maser garnered scientific acclaim, another brilliant mind entered the scene. Gordon Gould, a graduate student at Columbia University, had been independently developing his own ideas for a device that could amplify light through stimulated emission. Gould, recognizing the limitations of the maser, which operated only in the microwave region, envisioned a device that could extend this principle to visible light. He coined the term laser, an acronym for light amplification by stimulated emission of radiation, to describe his visionary concept. In 1957, Gould meticulously documented his ideas in a notebook, famously labeling it "Some Rough Calculations on the Feasibility of a Laser Light Amplification by Stimulated Emission of Radiation." This notebook would later become a pivotal piece of evidence in a protracted legal battle over laser patents. Maiman's triumph, the first laser beam. The race to build a working laser intensified in the late 1950s. While Gordon Gould faced setbacks in securing patents for his ideas, other researchers, notably Charles Townes and Arthur Shawlow at Bell Labs, were also making significant progress. However, it was Theodore Maiman, a physicist at Hughes Research Laboratories, who ultimately achieved the historic feat of constructing the first functional laser. On May 16, 1960, using a synthetic ruby crystal as the gain medium and a high-intensity flash lamp as the pump source, Maiman demonstrated the world's first working laser. The news of Maiman's breakthrough sent shockwaves through the scientific community. The laser, once a theoretical concept, was now a tangible reality, poised to revolutionize numerous fields. The science of light amplification, unlocking the laser's power. To truly appreciate the significance of the laser, we must delve into the fundamental principles that govern its operation. At the heart of the laser lies the concept of stimulated emission, first proposed by Einstein and later confirmed by Ladenburg. When an atom absorbs energy, it transitions to an excited state. In this state, the atom is unstable and tends to return to its ground state by releasing the excess energy in the form of a photon, a particle of light. This process, known as spontaneous emission, is random in nature, with photons emitted in various directions and with different phases. However, Einstein proposed that if an atom in an excited state encounters a photon with energy exactly matching the energy difference between the excited state and the ground state, it can be stimulated to emit a photon identical in wavelength, phase, and direction to the incident photon. This is the essence of stimulated emission, the process that underpins the laser's remarkable properties. A spectrum of lasers, from ruby red to semiconductor precision. Since Maiman's groundbreaking invention, laser technology has advanced at an astonishing pace. Today, a wide variety of lasers exist, each with unique properties and applications. These lasers can be broadly classified based on the gain medium used to achieve light amplification. Solid-state lasers, like Maiman's ruby laser, use a solid material, often a crystal or glass doped with ions, as the gain medium. These lasers are known for their high power output and are commonly used in industrial applications such as cutting, welding, and engraving. Gas lasers, on the other hand, utilize a gas or a mixture of gases as the gain medium. Helium neon lasers, emitting a characteristic red light, are a common type of gas laser used in barcode scanners and laser pointers. Carbon dioxide lasers, known for their high efficiency and power, find applications in materials processing, surgery, and even military applications. Semiconductor lasers, also known as diode lasers, are compact, efficient, and highly versatile. They are found in a wide range of electronic devices, including CD and DVD players, laser printers, and fiber optic communication systems. The diversity of laser types highlights the versatility of this technology. Lasers at work, transforming technology and our lives. From its humble beginnings in a physics laboratory, the laser has become an indispensable tool, transforming numerous industries and aspects of our daily lives. In medicine, lasers are used in a wide range of procedures, from delicate eye surgeries to the removal of tumors. Their precision and ability to target specific tissues make them invaluable tools for surgeons and other medical professionals. In communications, lasers form the backbone of fiber optic networks, transmitting vast amounts of data at the speed of light. These networks have revolutionized telecommunications, enabling high-speed internet, video conferencing, and countless other data-intensive applications. In manufacturing, lasers are used for cutting, welding, drilling, and engraving a wide range of materials with unmatched precision and speed. They have become essential tools in industries such as automotive, aerospace, and electronics manufacturing. Beyond these practical applications, lasers have also captured our imagination, finding their way into entertainment, art, and even our homes. Laser light shows, laser pointers, and laser printers are just a few examples of how lasers have become ubiquitous in modern society. As we venture further into the 21st century, the laser story is far from over. Researchers continue to push the boundaries of laser technology, developing new types of lasers with even more remarkable properties. Thank you for checking this out.